Hi, today we are going to start the IIT JEE revision of chemistry. In this video series, we are going to talk about the various important topics in chemistry. There would be some topics which are very important. There would be others which are not so important. I'll mention those as we go along. I'll mention the formulae associated with the different concepts, and we'll do some problems. We'll do some problems and some concepts which are, very important in terms of IIT JEE chemistry. So this is the agenda of this video. Now, chemistry in IIT JEE and otherwise has three broad parts. We're going to study each of them individually. The first is organic chemistry. Second is inorganic. And the third is physical chemistry. Now these are very important topics. I personally prefer organic chemistry as it's a quite easy topic. It is a very easy topic relatively as compared to others. Inorganic has some mugging to do. You have to learn a lot because you have to learn the preparation of various compounds and stuff. In case of physical, it's more formula based. So you'd have fun doing these stuff. Now, in this video, I'm going to start with organic chemistry. Organic chemistry, as we know, has the following topics. The most important topics which I am going to cover in this video are first is isomerism, which is quite important. The second is the various effects, also known as general organic chemistry, in which we'll have IE effect, that is inductive effect, mesomeric effect, resonance, etc., etc. The third, which will be the preparation, properties, and reactions of various organic compounds. And there's another topic which is not so important, which is glucose and polymers. Now one question, you can expect one or two questions from this, but not so many. Also, it's a very easy topic once you know the rest. These I would say isomerism is very important, and these effects are very important. Preparation is quite easy. You would need to know the various mechanisms here in order to perform well in the exam. And glucose and polymers is a rectification topic. You have to learn a lot of stuff in this. So now moving on, I'll begin isomerism. Isomerism. Now, there are two types. What is isomerism? Isomerism is basically compounds having same molecular formula but different physical or chemical properties. Now, so there are two types of isomerisms. The first is structural. The second is stereo isomers. Now, structural isomers. Structural isomers are of the following type. Number one is chain isomers. In this, basically, the length of the parent chain is different. So, what does this mean? Say we take the formula C4H10. So, it can have this configuration. It can also have this configuration, right? So these are the various isomers in case of C4H10. Another type of structural isomer is positional isomer. Positional. In case of positional isomer, the part of the subset or the functional group differs. The position of the subset. So basically, say we have a ketone, something like this. We have this thing, and we have a ketone here. Also, we have this thing, and we have the ketone here. So these are positional isomers. The position of the functional group is different in these two cases. So these are positional isomers. The third kind of isomers, structural isomer, is a functional isomer. In this case, the functional group is different. Example can be alcohol ether, ketone aldehyde, etc. So we can say this, like this is a ketone and this is an aldehyde of the same formula. The next type is a metamerism. What is metamerism? In metamerism, we have the same functional group, but it has different number of carbon atoms on either side. Different number of carbon atoms on either side. So, an example of this can be this. We can have the functional group, say ketone, and we have this. Let's pick this again. So this and this are metamers of each other. The functional group here is ketone, but the number of carbon atoms on either side here is 2 and 2. Here it is 3 and 1. So these are metamers. You notice that these are also positional isomers, but one pair can fit into various categories here. Like it can be both functional isomer, metamer, not metamer. It can be both metamer and positional isomer and chain isomer. So the various possibilities exist in this case. The next is next in the final category is tautomerism. Now tautomerism is something which is very important, and we'll deal with it later and very deeply with this, because one topic you can expect at least one question from this in IIT JEE. That's what I have observed in my paper at least. So next we move to the other type, which is stereoisomers. Stereoisomers are of two types broadly. There is conformational and there is configurational. Now, conformational is again of two types: optical isomers and geometric isomers. Configurational, on the other hand, is of two types. The first is rotational, rotation about single bond, and the second is amine inversion. Okay, so now that we have divided the various types of isomers, we are going to proceed to degree of unsaturation. Now, what is degree of unsaturation? Degree of unsaturation basically is the number of double bonds or triple bonds which are present in a compound. Okay, the number of double bonds or triple bonds present in a compound. So I'm going to give you the various formulae to calculate the degree of unsaturation. Now, first is for CXHY. For CXHY, the degree of unsaturation is X plus 1 minus y by 2. Second is CXHYOZ, degree of unsaturation. Degree of unsaturation in this case would be x plus y minus y by 2, the same as the previous case. The third one, which will have its CXHYXM. Now, CXHYXM would be something like this. It would be x plus 1 minus y plus m by 2 du. Here x is some other atom other than nitrogen, oxygen and hydrogen. X is not hydrogen, oxygen and nitrogen, something other than that. And the fourth formula is CXHYNP, where N here is nitrogen. The degree of saturation in this case is x plus y minus, in the bracket, y minus p by 2. This is the degree of unsaturation. And the fifth and the last formula is CXHYOZ XMNP. So it contains all the above formula, and we can put in the values and get the result accordingly. So it is x plus 1 minus y plus m minus p by 2. So you can get all the other formulae from this formula. So this is degree of unsaturation. So what does degree of saturation basically mean? It means when degree of unsaturation is 0, it's an open chain saturated structure. Open chain saturated structure. When degree of unsaturation is equals to 1, it means double bonded system or ring system. And finally, when degree of unsaturation is equals to 2, it means 2 bond, 2 double bond, or 1 double bond plus 1 ring, or 2 rings, or a triple bond. Okay, so this is degree of unsaturation. Now we'll see some examples, illustrations or examples of degree of unsaturation type of form questions. So the first is C3H6. C3H6. So the degree of unsaturation in this case is 3 plus 1 minus 6 by 2, which is 1. So degree of unsaturation is 1, so it is something like this: C double bond C C, or it can be a ring structure. So these are the two types of structural isomers which are present in this case. Another example which we can look at is C4H8. Here degree of unsaturation is 4 plus 1 minus 8 by 2, which is again 1. So we'll get something like this: C double bond C C C, or C C double bond C C. These are positional isomers. Or we can also have a chain length isomer, and we can have something like this as well. We can form one ring, and externally we can have a CH3, or we can form this. So these are the various kinds of structural isomers which we can have for this case. Next is Next, we look at stereoisomerism. This is all about structural isomerism, which we'll look at metamerism and tautomerism later, because those are separate topics and very important topics as well. Now we go into stereoisomerism. Now, stereoisomerism is compounds having same type of molecular formula, structural formula, but different spatial arrangement, that is, the configuration or orientation in space is different. So, as I mentioned earlier, there are two types. The first is structural and the other one is, the first is conformational and the other one is configurational. Conformational, configurational. Conformational are convertible, that is, they can go from one form to the other, whereas these are non-convertible. Now, we'll look at conformational isomers now. Conformational isomers, different forms of the compound arises due to rotation about single bond. So, single bond rotation happens. In this case, individual existence of a conformer is different. We cannot have, it's not possible actually. We cannot have ethane in which the various hydrogens are rotated at specific angles. We cannot have that kind. We cannot ever say that this is the form which is present in nature. So it is difficult to have, it is impossible to have individual isomers, individual conformations of individual existence of different conformers. Now, there are various types of representations which we are going to talk about. So, the representations are, there is Newman representations, there is Newman's representation, and there is a sawhorse representation. So, what is Newman's representation? Newman basically states this: if we have CH3, then it can be represented something like this, with the circle, so this is hydrogen, 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 hydrogen. This is the staggered form, and we can have sawhorse, which is something like this. Hydrogen, hydrogen, hydrogen. Okay, so these are the types of representations which we can have. Now we begin with the conformations of ethane. Now, conformations of ethane. We'll see this example so as to get a better understanding of conformational isomers. So in case of ethane, we have CH3, CH3. So it's a double bond, and rotation can take place across this double bond. So we can have these forms. We can have in the Newman projection something like this. This is hydrogen, 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 and the other hydrogens are also behind these particular hydrogens. So this is one form possible. Now this is another form possible. Also this angle can be anything. Now these angles can change, and so we can get infinite number of conformational isomers. It all depends upon the dihedral angle. In this case, the dihedral angle is 0 degree. In this case, it was 60 degree. So, in case of 0 degree, it is known as the eclipsed form. It is known as the eclipsed form, and this, in case of 60 degree, it is known as staggered form. Now, eclipsed form is basically when we have the hydrogens behind each other, and staggered form is when we have the hydrogens at 60 degree from each other. So basically 0 degree, 120 degree, 240 degree and 360 degree are all the same, and in this case 60 degree, 180 degree and 300 degree are all the same. If it's quite an easy thing to understand. Now, all intermediate conformations are known as skew forms. That is, they exist and there are infinite number of them. The important part in this concept is the stability. Is the stability of stereoisomers. So the stability order is staggered, greater than skew, greater than eclipsed. Staggered is when they are at maximum possible distance from each other, the hydrogens. Skew is when at any other angle other than 60 degree and 0 degree, and eclipsed is at when they are behind each other. Eclipsed form is unstable because of more repulsion between hydrogens, that is van der Waals force, and second is more torsion strain. Okay. Now, the van der Waals repulsion occurs between atoms or groups of atoms. This repulsion is due to van der Waals. It can happen between atoms and groups of atoms. Okay. Now, torsion strain is the repulsion between bond pairs in eclipsed form. There is no torsional strain in case of staggered form. Here we have no torsional strain. Okay. We can have the potential energy diagram, which is something like this. This is the potential energy. Here we have the dihedral angle. So the potential energy would be something like this. So this is at 0 degree, this is 60 degree, this is 180 degree, this is 120 degree, this is 0 degree, and so on and so forth. So this is the potential energy diagram. The high peaks of potential energy are the eclipsed form, and the low peaks are the staggered form. The energy difference between the staggered and eclipsed form is called the conformational energy. So this difference is known as conformational energy, and is 12 kilojoule per mole for ethane It is also known as torsional strain energy. So these numbers are not important. We can okay. So next I'll show you an example of how to draw conformational isomers, because you can get this in the exam. So as a MCQ. So we'll draw the conformational isomers of propane. So conformations of propane. Propane is this. So we'll do the conformations of this. So we'll have something like this. We'll imagine the rotation about this single bond. It's the same. We can consider the other one as well. So it's the same. It's the same thing. So in human form, it is something like this. So we have CH3 here, H, 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 H. This is the eclipsed form. We can have something like this. Hydrogen, hydrogen, CH3, H, H, H. This is the staggered form. So it is basically the same. We can also have, we can do it for a lot of compounds, but that is not important. We can, the next we'll see it for N-butane. N-butane has a different concept in case of conformations. N-butane. N-butane is this compound. So this rotation, there can be two types of rotation. There can be a rotation along this, or there can be rotation about this. So we'll when it happens about this, it is the same as the previous case. So we'll consider rotation about this. That is the middle single bond. How does it happen? So various forms are. So we can have CH3 here, H, H, CH3, H, H. This is the fully eclipsed form. That is, the same molecule is behind each other. CH3 is behind CH3, H is behind H, and so on. The second possibility is this, CH3, CH3, H, 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 H. This is Gauch form or partially staggered form, as it is also known. The second possibility is this. The third possibility is this. We can have CH3, behind it is H, H, CH3, H, H. Okay, so this is known as partially eclipsed form. It is also, this is partially eclipsed. This was partially staggered. And finally we can have this form, CH3, opposite to this CH3, H, 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 H. This is known as fully staggered. Or anti-form. As it is quite evident because of torsional strain and repulsion, the stability order is something like this: anti greater than gauge, greater than partially eclipsed, greater than fully eclipsed. So this is the stability order. Okay. The conformations in between, as I have already said, are known as skew isomers. Now, this marks the end of this topic. Next, this is the end of conformations. As we next we move to the next topic, which is cyclohexane. Cyclohexane has various forms, the boat and other stuff, which we'll come to now. Cyclohexane. Cyclohexane is the most important conformations of cyclohexane are in the chain form, chair form, boat form, half chair form, and the twist boat form. So there are chair form, boat, half chair, and twist boat. So these are the forms of cyclohexane which are present. The most stable is the chair form. The most stable conformation is the chair form. Stability order is chair greater than twist boat, greater than boat, greater than half chair. So I'm going to draw the various forms, and then you can get a feel of how these conformations occur and why the chair form is the most stable amongst these. So the first is the boat form. So the boat form is something like this. Here this hydrogen is here and here. Something like this. So this is known as the boat form. It is less stable because of flagpole interaction. What is flagpole interaction? Flagpole interaction is basically this. This is a flagpole interaction. This hydrogen here and this hydrogen here, there is a repulsion between these. This is 1 hydrogen and this is 4 hydrogen. So 1, 4 repulsion between these two hydrogen is the reason due to which it is less stable. This interaction is removed in case of twist boat, which is why twist boat is more stable as compared to the boat form. The next is the chair form. Chair form is the most stable. Chair form, the diagram is something like this. So we have hydrogen, 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 something like this. The straight hydrogens are the axial hydrogens are up down as we go along, like so here it is up, here it is down. And the equatorial hydrogens are parallel to the opposite side. So I'll show you what it means just a sec. So what I mean is this hydrogen here, it is parallel to this line, and these are opposite to each other, like this and this and this. So one is up, the other is down, one is up, the other is down, something like this. You know what I mean. So this is the chair form. Chair form is very important and very stable. So these are known as axial hydrogens, and these are the equatorial hydrogens. Okay. Now cyclohexane is more stable because all the carbon are sp2 hybridized. sp2 hybridized carbons. And they maintain their volatility of being arranged in tetrahedral orientation, and the bond angle remains 109 degree. They maintain their identity of being arranged in tetrahedral orientation. the bond angle here is 109 degree, which makes it very stable. Okay. Now, next is the boat, and the twist boat is basically a form of the boat in which the flagpole interaction is not there, and the half chair is something like this. It is this. It is in the chair. It is in the form of a chair. So it is something like this. The diagram is not important. The thing is, in that case, the bond angles are different. Bond angles are such. There is a lot of torsion. So you can get an MCQ which will ask you, why is the chair form more stable as compared to the half chair form? The reason is the bond angle here is 109 degree, and that is tetrahedral orientation, due to which it is very stable. In case of half chair form, it is not very stable because the bond angles are much more stringent, due to which the ring structure is not well supported. Okay. Next we come to geometric isomers. The next topic is geometrical isomers. Now, it is basically a configurational isomer, stereoisomers, which arises due to different arrangement of atoms. So, it is configurational stereoisomers. They arise due to different arrangement of atoms or groups of atoms around a system. In this case, rotation is restricted. So they are non-interconvertible at room temperature. Okay. So in case of alpha bond systems and cyclic systems, the free rotation is restricted, and in those cases geometrical isomerism is possible. So in case of pi bond system and cyclic systems, so it happens in case of pi bond and cyclic systems. Okay. Now, geometrical isomerism in pi bond systems. Pi bond systems. Now, pi bond systems are systems in which the carbon-carbon have a double bond between them. So this is a pi bond system. So it is generally represented in this way, and it looks something like this. These are the pi connection, and these carbon would then be associated with some other elements, other atoms or groups of atoms. Now, the condition for geometrical isomerism in pi bond systems is that each carbon should be attached to two different groups. That is, in this carbon, the group should be different. It should be A and B. It cannot be A and A. So that is the criteria which we have. And this carbon also, the same thing should be there. It should not be the same group. So this is the condition for geometrical isomerism in pi bonded systems. Next is cyclic systems. Now, in case of cyclic systems, it is very difficult to have transform. Very difficult. That is because of the angular strain associated with the transform. Now, when we have something like this, this is a 3 bonded cyclic system, and this is the double bond here. Now, say we have a hydrogen attached here and a hydrogen attached here. So it is very easy to form this, and these hydrogens will not have much strain because these angles are big. Now, if we have something like this, these are the double bonds, and this is the hydrogen, say here, and this is the hydrogen, say here. So this is not how it will actually look like. It will then look like something like this. Double bond, carbon, hydrogen, and the same carbon should be here, and hydrogen. So this carbon is actually the bridge carbon. So it is very difficult to maintain this angle here. This angle becomes very high and this angle becomes very high, and there is a lot of angular strain. It is usually seen that in cyclic systems, geometrical isomerism occurs for greater than 7 carbons, greater than equals to 7 carbons. I'll show you an example now. An example of this is something like this. Say we have this 8 bonded system, 8 carbon system, cyclic, and this is the double bond here. So we can have hydrogen here and here across this double bond. So this is the cis form. So how will the trans form look like for the same compound? For the trans form, this is the double bond, right? This is the hydrogen here and this is the hydrogen here. This carbon will be the same, this will be the same, this will be the same, and this will be the same. Same for here. Have this, this, this. And this carbon here will be joined to this carbon. So it will look something like this, basically. Double bond, here, 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 here. Double bond, here, this, and this is a bridge. So this, and finally this. This is the hydrogen, this is the hydrogen. Here the angular strain can be maintained and therefore this trans form exists. In the case of less than 7 carbons, the trans form cannot exist. Now, next we talk about the configuration of geometrical isomerisms. Configurations. Now, the first type is cis-trans. So, we all know that cis is having same groups at the same side. Same groups on same side. And trans is same groups on opposite side. On opposite side. That is cis-trans. Another way of characterizing the geometrical isomerism or naming them is EZ configuration. EZ configuration or Kahn-Ingold pre-log system basically uses seniority as a way of representing the configuration. Seniority. So in case of E, senior groups are on opposite side. And in case of Z, on same side. So, you must be wondering, how is this seniority determined? How do we know which group is senior? So, there are some rules for seniority assignment. Rules for seniority. So first is the atom having the larger atomic number is senior. So as Z, that is the atomic number, increases, seniority increases. So nitrogen is more senior than carbon because the atomic number is 7 and this is 6. Okay. Next is, in case of isotopes, then that isotope is senior which has higher atomic mass. Say we have carbon 12 and carbon 14. So carbon 14 is senior as compared to carbon 12 because of its higher atomic mass. Okay. So this is how we determine seniority. Now in case of groups, that group will be senior in which there is a free atom. What do you mean by that? It means OH. So groups in which connecting bonder is a connecting bond atom element is senior. So let us consider the example of this methyl group and the hydroxyl group. In case of the methyl group, it is carbon's single bond which is going to be attached to the group, and in case of hydroxyl, it is the oxygen's bond which is going to attach. So oxygen is the oxygen is more senior as compared to carbon, which we get from this first rule, and therefore OH would be senior as compared to CH3. Okay, this is the rule for seniority. However, when the first atom is same, then we go to the next bonded atom. So say we have something like this. We have CH3 and we have CH2. Okay, CH3. I'm sorry. We have something like this. We have CH2, CH3. So which of these will be senior? This will be senior. The reason is the first element here is carbon and here also is carbon. So next we go to the other bonds. So here the three hands contain hydrogen, hydrogen and hydrogen. Here there are two hydrogens and one CH3. So this carbon is senior as compared to hydrogen, and therefore this group is senior. Okay, so this is all about seniority. Now, how to assign EZ configuration? Now that is the important question, and we'll look at a few examples of that. Assigning EZ configuration problems of EZ. So let us take a first example. Say we have C, double bond C, CH3, C2H5. Here we have hydrogen. Here we have deuterium, which is an isotope of hydrogen. Now, first you will notice that this is a this compound exhibits geometrical isomerism because each of the carbons have different groups attached to them. Here is hydrogen and deuterium, and this contains methyl and ethyl groups. So now we come to E and Z. So in this case, deuterium is senior group, and in this case, ethyl is a senior group. Now they are on the same side. So it is a Z configuration. Let's take another example. Say we have this group. We have deuterium, carbon, hydrogen, double bonded with carbon, CH3, and this is carbon star, carbon 14, that is CH3. So which will be senior? So in this case, deuterium is the senior element as seen in the previous example, and carbon 14 is senior, and now they are on opposite sides. So this is a E configuration. Similarly, we can do all other examples. This is a very simple concept. The next concept we'll look at is optical isomerism. Now, optical isomerism, it contains concepts like plane polarized light, whether a compound is optically active or not, and dextrorotatory, levorotatory and stuff. So first is whether optically active or not. Second is D or L. So these are the questions which we are going to answer. Now, we are not, there are concepts like chiral carbon. What is a chiral carbon? A chiral carbon is a carbon compound having 4 different groups attached to it on all 4 hands. Carbon has 4 hands, okay? It can bond on 4 sides. Now, all of these should contain different groups of atoms or atoms for it to be a chiral carbon. Okay, this is the definition of chiral carbon. So, let us see an example. Say we have something like this. This is a chlorine and this is C2H5. So, determine whether this compound has a chiral carbon or not. Now, let us look at this carbon. This one here. Now, it contains 3 hydrogens. So, this is not a chiral carbon. This one, it contains 2 hydrogens. So, it is not a chiral carbon. 2 groups are same. This one, it contains 1 hydrogen, 1 ethyl group, 1 group containing a chlorine, and another ethyl group. So these 2 are same. So this is not a chiral carbon. And lastly, this carbon, this contains a chlorine group, a hydrogen group, a big group containing C2H5 and another C2H5 diethyl group, and this is a methane group. So this is a chiral carbon. So this compound has a chiral carbon. Having a chiral carbon is a criteria for having optical activity. If you have chiral carbon, if you do not have chiral carbon, you cannot be optically active in some sense. But if you have chiral carbon, it does not mean you are optically active. It's not a if and only if condition. It's a if and only if condition, but not double implication. Now, what are the requirements for optical activity? The first is it should be dissymmetric molecule or compound, or always optically inactive. So, if it is compounds which do not contain compounds which contain a plane of symmetry are not optically active. So, no plane of symmetry. Second is there should be no center of symmetry. So these are known as compounds containing these 2 conditions are known as dissymmetric. That is, when we have one which has plane of symmetry and one which has center of symmetry are known as dissymmetric. So asymmetric, which is the opposite of dissymmetric, are compounds which do not contain these, and these are optically active. Now, let us look at Fisher projection formula. That is the way of representing optical isomers. Fisher's projection formula. Fisher's projection formula, you may have seen diagrams like this to represent a compound. This is OOH, CH3, hydrogen, say C2H5. So, this carbon is chiral carbon. Firstly, we have to see that whether it is chiral carbon or not. So, this is a chiral carbon. So, this is optically active and it will have an enantiomer which looks something like this. Basically, it's mirror image. These are enantiomers. That is, they have mirror image relationship. Now, next we'll look at the wedge and dash formula. What is the wedge and dash formula? It is also a way of representing chiral carbons. How does a wedge and dash look like? Wedge and dash formula. So, we have the chiral carbon. We have, this is the parent carbon chain. So, this extending up to here is the parent carbon chain. This is above the plane of the board and this is below the plane. That is, this is below. So this is how we represent a chiral carbon in wedge and dash form. This is below, this is above, and this chain is the parent chain. This is the parent chain. This is a wedge and dash formula. Now, to go from one enantiomer to the other enantiomer, we just have to take the mirror image. So, in this case, there was a ethyl group. This is a ethyl group. So, the mirror image would look something like this. We'll have a carbon. This is the above. This is the below. This is the enantiomer, and this is the ethyl group, and this is the long chain. So these are enantiomers. So basically, we have to take the mirror image to draw the enantiomer. Now, the next topic is how to convert, how to look at the RS configuration. So this is the third type of configuration which we are looking at. Let me write that down. RS configuration. Now, what does RS configuration mean? R is rectus and S is sinister. Now, enantiomers have different arrangements or configuration. So, how do we know whether it is R or S? So, one way of remembering this is VCR, HCS, VAS, HAR. Now, what does this mean? I'll let you know what it means. So, let us say, how do we do this? So, we assign priority to the groups. As we have determined the seniority, this is equivalent to seniority in some sense. So, the rules are same and there would be some additional rules in this case. So, let us say, let us look at an example to make it more clear. We have the Fisher projection formula, something like this. This is the C2H5, CH3, COOH and H. Now, the most senior group here would be this carbon or this carbon or this carbon. So first we assign the highest seniority. Highest seniority would be this carbon. Why? Because the second to this carbon is oxygen, which has higher seniority as compared to hydrogens in this case. The second senior group would be this, ethyl. The third would be this, and the fourth would be this. Now, from the first group, we go towards the fourth group. So, we run the cycle something like this. So, we are going clockwise. Clockwise. And the lowest priority group is vertical. Hydrogen. This is the lowest priority group and it is in the vertical position. So, vertical. Now, V, C. So, what is the configuration? We look at here. It is R. So, it is rectus. Rectus configuration. Similarly, we can do other examples related to this. Now, Fisher projection formula has one rule for calculating for computing whether it is R or S. So, in a Fisher projection formula, let's say we have this H, Cl, Br, I. Now, if we make odd number of conversions, then we get the enantiomeric pair. But for even number, it remains the same. It remains same. What is meant by this statement? It means that we can do this. We can replace these two, this hydrogen and water, this hydrogen and bromine, and replace these together. This is hydrogen, this is bromine, this is iodine and chlorine. So this and this are similar to each other. But let us say we have something like this. We replace this hydrogen with the bromine, but we make no changes to the chlorine and iodine's position. So these are not the same. These are not the same because this is an odd conversion. We have made only one change. This is an even conversion. We have made two changes. So this is the rule for changing the hands of a Fisher projection formula. Next we come to compounds having two chiral carbons. Compounds with two chiral carbons. Now, let us say we have something like this. This is hydrogen, CH3, bromine, chlorine, CH3, hydrogen. So we have something like this. This is a chiral carbon here, and this is also a chiral carbon. So there are two types possible. It can be an enantiomeric pair or it can be a diastomeric pair. Okay, so this is a compound with two chiral carbon, and a subset of this is two non-identical chiral carbons. Now, this is an example of non-identical chiral carbons. Non-identical chiral carbons. Say we have this CH3, Br, Cl, H, CH3. So these are non-identical chiral carbons because one group is bromine here, and here one group is chlorine. So we place a mirror here and we draw the enantiomeric pair. This will be hydrogen, bromine, chlorine, CH3, CH3. So this is the erythro, this is the hetero pair. Erythro, there is a Y here. It's an erythro pair. Another possibility to this is we have something like this. We have, this is a CH3, Br, H, chlorine, and place the mirror here. We get CH3, H, chlorine, and Br. So this is the third and fourth type possible. This is the trio pair. That is same group on different side. Erythro pair is same group on same side. So this are 1, 2, 3 and 4. Let's name them 1, 2, 3 and 4. This here is a 1. This is 2. This is 3. And this is 4. So which are enantiomers and which are diastereomers to each other in this context? So we have the following combinations. We have 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and finally 3 and 4. Now 1 and 2 are enantiomers to each other because they have a mirror image relationship. Similarly, 3 and 4 are enantiomers because they have mirror image relationship. Whereas the rest of them, they do not have mirror image relationship with each other, but they are optical isomers of each other. So these are diastereomers. Okay. So this is how we define enantiomers and diastereomers. The ones which have mirror image relationship and the ones which do not have mirror image relationship. Now, next we move to compounds having two identical chiral carbons. So in that, two identical chiral carbons. So let's say we have this compound COOH, OH, H, OH, COOH. So these are both chiral carbons, and there exists a mirror image relationship between these now. COOH, H, OH. So this is the possibility. So these are enantiomers to each other. Now another possibility is the mesoform, which is achiral. We can have something like this. COOH, COOH, HOH. That is the same group on same side. Now, but notice in this compound here, we have something odd. We have a plane of symmetry here. If you look up and down, they have it is a plane of symmetry here, because of which it is not optically active. So it is achiral. This form of this compound is tartaric acid. The form of this compound in which it is achiral is known as the mesoform. So mesoform is quite important. Sometimes you'll get questions like they give you a compound and ask you how many optically active isomers are possible. So if you make a mistake and you add this mesoform to the number of optically active, then you lose a mark. So basically it is you have to notice whether there exists a plane of symmetry or not. Okay. But another important part is, let's name this 1, 2 and 3. Now 1 and 2 are enantiomers to each other, but 1 and 3 and 2 and 3 are diastereomers. They are still diastereomers even though this compound is in mesoform. Okay. Next we move to allenes. Now, what are allenes? Allenes are compounds having triple carbons with double bonds between them. So we have something like this, T, P. Now, in this compound, it is when you represent it in this manner, it is very difficult to notice the plane in which A and B are located in these. But to give you a fair idea, it is represented in this manner. So this is A here. This is B. We get a dashed A here and a solid dash here for this B. The reason is because in this compound we uses the dxy and dxz for this one. This and this, when they form the pi bond, it uses up the dxy and dxz of this, and therefore when it forms a pi bond with this, it uses the dz square. So they go out of plane. Okay, so that is why these are out of plane. You can consider a plane of this manner. So the entire thing is in this plane, but these two are either above it and below it. So it is in this manner. This is A and B in this case. The rest of it is in plane. Okay. So the reason two bonded systems do not have optical activity, because they are all in the same plane. So this is a plane of symmetry. There is a plane of symmetry here, due to which it is optically inactive. But allenes can be optically active because of the existence of no plane of symmetry. This A and B are out of plane. The condition for allene having optical activity is that this compound, this carbon and this carbon, they should have different groups attached to them. The same condition which was there for geometrical isomerism. Different groups attached to them. Okay, groups of atoms or atoms. Now let us look at a few examples of determining whether an allene is optically active or not. Say we take up this example. This is CH3H. CH3H. Add another CH, C here. So we get CH3 and H. Now, this is also known as an allene. Allene is any carbon double bonded system which has more than 3 carbons, more than or equal to 3 carbons. So this is also an allene. Now we have to determine whether or not it is optically active. So, now all these carbons are in the same plane. They are all in the same plane. Let us say this is also beyond. This is also above the plane. This carbon group will also be in the same plane, because let's say this is the XY and XZ forms. Here, this carbon here will use up its dz square to bond with this dz square. So now this carbon has dxy and dyz available to it, and therefore these are also in the same plane. So there is a plane of symmetry here, due to which it is optically inactive. Okay, next we move to DL configuration. The same logic the same logic can be applied to spiro and biphenyl compounds also. Spiro and biphenyl compounds, they have the same logic as allenes. That is, one group is out of plane, the other group is in plane, and you have to find whether there is a plane of symmetry or not. Okay. So next we move to DL configuration, dextro-levo. So far we have seen cis trans, EZ, RS, and now we move to DL configuration. DL configuration is also known as relative configuration because here all configurations are deduced using standard compound, that is glyceraldehyde. Standard compound is glyceraldehyde. Okay, now let us look at an example. Glyceraldehyde is actually this OH C CH star OH CH2OH. Notice we have a chiral carbon here. Now this is so it can be represented in this form. CHO Now, this is the D form. We have another possibility using a mirror here. We get CHO, CH2OH, H, and OH. As a rule of thumb, we always place the aldehyde group on the top of the vertical line. So this aldehyde group is on the top of this vertical line. And therefore, when the OH group is on the right, it is dextro. When it is on the left, it is levorotatory. Okay, so this is how we characterize D and L. This completes the optical isomerism topic and hence the isomerism in general. These are the important topics in isomerism. You can also read about the spiro and biphenyl compounds, which are very easy to understand. Next, we will do another topic. Thank you. The next topic is general organic chemistry. Now, in general organic chemistry, we'll be dealing with the following topics, which are very important, along with a few examples of each of them. The first is the effects. That is inductive effect, hyperconjugation, resonance, and mesomeric effect. Okay, and secondly, we'll deal with the mechanisms and the energies of various carbocations, carbanions, and free radicals. Okay, So without further ado, let's begin with the inductive effect. Now, what is inductive effect? Inductive effect is basically when an atom or a group of atoms attracts electrons more strongly other than the atom with which it is attached. Say we have a carbon attached to a iodine group. So iodine is very electronegative. So it will attract the electron pair which is present in the middle towards its side, and so there will be a delta negative charge over iodine and a delta positive charge developed over carbon because of dissymmetric electron sharing. And therefore that will lead to the development of delta charges, and this is known as the inductive effect. So there are two forms of inductive effect. The first form is minus I effect. Now what is minus I effect? Minus I effect basically states that any atom or group which attracts electrons more strongly than hydrogen. Any atom or group which attracts electrons more strongly than hydrogen is one which has minus I effect. The order of the effect is, that is, the strength is minus NF3, the plus sign on N, greater than minus N R3 greater than NO2, cyanide group, C double bond H greater than the keto group, which is greater than the acid group, then acid group connected ester group, amine greater than fluorine, chlorine, bromine, iodine, minus OH greater than C triple bond CH greater than minus phenyl, not minus phenyl, greater than phenyl, which is in turn greater than the ethene group. Okay, so this is the order in which the minus I effect proceeds. Next we'll look at the plus I effect. Plus I effect, that is atom or group of atoms which attracts less strongly the electrons than hydrogen. Attracts less strongly than hydrogen. The order is, we have O minus greater than this group, the O minus here greater than Me, C, that is tertiary methyl group, this greater than Me, which is in turn greater than the methyl group CH, which is greater than the methyl group CH3, greater than tritium, deuterium greater than hydrogen. So this is the effect of this is the order of plus I effect. Generally, the inductive effect is lost after 3 carbon atoms as the distance increases. So inductive effect is lost after 3 carbon atoms. Now, also, what is the application of inductive effect? So we can use inductive effect to determine whether the intermediates are stable or not. So we look at the application. The application of inductive effect. The first one is stability of intermediates. What is meant by stability of intermediates? A carbocation is one which has electron deficient group or atom. So first we define what a carbocation is. Carbocation, electron deficient atoms or group. So it is basically carbon having a plus charge on it. So this one, if it is attached to a group containing group G, and this group G has plus I effect, then it increases the stability of the carbocation. Now this is very easy to understand because the carbocation has a plus charge on it. So this plus charge is basically means electron deficiency. So when the plus I effect group pushes the electrons towards the carbocation, it increases the stability. Similarly, if the same carbocation is attached to a minus I effect group, then it decreases the stability. This is the group G. Minus I effect. It will pull the electrons more, and this plus charge will increase, and therefore decreases the stability. So this is the first application. The stability of carbocation is inversely proportional to the minus I effect and directly proportional to the plus I effect. Okay. So let us look at an example of stability of carbocations. Stability order. Example. So we have CH3, CH2, CH2 plus. This is the first group. Then we have CH3, CH, CH2, and there's a chlorine attached here. And the third one is CH3, CH2, CH2 plus. And this is the, okay, let's make this CH2. And we attach a chlorine here. So these are the three groups available to us. This is A, this is B, and this is C. Now, in case of A, we have an ethyl group. Here. In case of B, we have an ethyl group with a chlorine attached here. Now, this chlorine is one which has minus I effect. So chlorine has minus I effect with it. So it will pull the electrons towards itself. So chlorine shows minus I effect, and also as distance increases, the minus I effect decreases. So which is the most stable? It will pull the electrons towards itself this way. Therefore, there will be a delta positive charge here, and so it will try to pull the electron towards itself. So A will be the most stable, then C, and then B. This is the order of stability. Okay. Resonance. Now, what are the characteristics of resonance? It occurs only in case of conjugated electron systems. Conjugated double bond systems. Okay. So, in resonance, basically there is electron jumping from one form to the other, and we do not know the exact position of the double bond. Let us take an example. Say we have this. So this is a conjugated electron system. There's a double bond, then a single bond, and then a double bond. Okay. So we can say that this double bond will jump here, and this double bond will open up here. So it can look something like this. H2C, single bond CH, double bond CH, single bond CH2 minus. Okay. Also, it can happen in the reverse order. We can have this double bond jumping here and this falling here. This falling here. So it will look something like this then. H2C minus CH, double bond CH, CH2. Okay. Now since this double bond is shifted, this will become plus here and this will become plus here. So that is pretty obvious. Now, so basically it is a delocalization of alpha electron in a conjugated electron system. Delocalization of pi electron. Delocalization of electron in a conjugated system. Okay. So next we look at the stability of resonating structures. Stability of resonating structures. I am skipping the topic of how to draw the resonating structures because there is very limited possibility of a question from that part, because it is a very obvious topic. You can understand it this way. This is benzene, so this is a possible resonating structure. This is a possible resonating structure, and this is also a possible resonating structure. So these are the resonating structures of benzene. So it is very obvious that this will not be actually asked in the exam, but theoretical knowledge of this concept is very important because it will be useful while determining the stability and energy of resonating structures. Okay. So the first point in this is, number one, neutral resonating structures are relatively more stable than polar structures. Neutral resonating structures are more stable than polar structures. An example of this can be shown in this manner. Say we have CH2, double bond, CH, double bond, C. This is H. Sorry, there is no H here. So this is CH, CH2, double bond CH, single bond C, double bond O, and this is H. Now this is a neutral structure. This is neutral. If we look at a polar form of this type structure, in the polar type, what will happen is this will shift here and this will shift here. So we'll get something like this: H2C, single bond CH, double bond C, H, O minus, this is plus. So it becomes a polar structure. This here is polar. Now this is less stable as compared to this neutral structure. Okay, this is the first point. The second point is the resonating structures having more number of covalent bonds are relatively more stable. More covalent bonds means more stable. So let's say we have something like this: CH3 C plus double bond O. Okay, and a resonating structure of this is of this form. We have CH3 C triple bond O plus. So this has 4 covalent bonds, while this has 3 covalent bonds. Both are polar in nature, but this has 4 and this has 3, and therefore this is more stable as compared to this. More stable, less stable. Okay. The third point is resonating structures having electron deficient atoms. Like we have this electron deficient atoms. We have plus here. This is OH, and we have something, a resonating structure of this is this. We have double bond O here with a plus sign and H. Now this is more stable. This is more stable as compared to this, because in this case, because of the electron deficiency, when the plus sign is on the oxygen, it completes the octet of carbon. This carbon here, its octet is completed in this case, but in this case it is a carbocation. It has only 3 hands. So the 4th hand is a plus sign. So octet completion implies more stability. Okay. Now, also the fourth and the last point of this stability portion is resonating structures having charge separation will be relatively stable if the charges are far apart. Say we have charges should be away from each other and negative charge should be on more electronegative atom, and positive charge similarly on more less electronegative atom. So let us look at an example of this. We have CH2 double bond. We have a CH2 double bonded with a CH, that with C, double bonded O and H. A resonating structure of this will be of this form. CH2 plus, single bond CH, double bond C, double bond, single bond O minus H. This was seen previously also. So in this case, 2 will be less stable as compared to 1. So 1 and 2. So 1 is more stable as compared to 2 because of charge separation part. And in this case, let us take another possible resonating structure. We have, say, something like this: CH2 CH CHO plus, this is the double bond here, and this is CH2 minus. So we have a carbocation and an oxygen with a plus charge on it. Now in this case, 1 is obviously more stable than this third part also because of non-polar nature of 1. But in case of 3, the positive charge is on oxygen and the negative charge is on carbon. Oxygen is more electronegative and carbon is less electronegative. In this case, the positive charge was on carbon and the negative charge was on oxygen. So 2 is more stable than 3. And these are both less stable than 1. So this is the stability order for this compound. Okay. Next we move to factors affecting resonating energy. Factors affecting resonating energy. Now, compounds or ions having equivalent stable resonating structures have relatively high resonance energy. What is meant by this? Compounds having equivalent resonating structures have relatively high resonance energy. This is a very important point because seldom I have seen a question in the JEE paper. It was there in JEE 2009 and 2011, a question on resonating energy in which compounds having equivalent resonating structures were compared. So let us look at an example for this. There was, let's say, CH3 C O minus double bond O. So the resonating structures are CH3 C double bond O minus and O here. Sorry, there will be no minus sign here. There will be minus sign here. So this is the resonating structure, and another resonating structure is. So these are the two resonating structures. So next we will look at the overall resonating form. So resonating form will be of this kind: CH3 C dash. This is O. This is O. This is delta negative, delta negative. So this is the overall resonating structure. Now these are equivalent resonating structures. This and this are equivalent to each other because they are the same compound. Basically, we are replacing the position of the double bond, but we get the same compound. So this overall resonating structure will have relatively higher resonance energy. Okay. Second point is the number of resonating structures isn't important while stability of the resonating structure is important. Now, say we have many resonating structures. So it does not matter in the computation of the resonance energy. The reason is we take the average of all those structures. So some will be more in energy and some will be very less in energy. And so when we take the average, the resonance energy comes to a stable point. The number of resonating structures is not relevant in energy considerations. Okay. So this marks the end of resonance effect. Next we move to the mesomeric effect. We'll look at the application of all these effects at once in several multiple choice questions. So next is mesomeric effect. What is mesomeric effect? Mesomeric effect is a resonance effect in which there are groups instead of atoms. Ability of an atom or a group to delocalize pi electrons of a conjugated system through resonance is known as mesomeric effect. So basically it is a resonance effect by a group. So there are two types of mesomeric effect. There is plus M effect. So plus M effect, if the transfer of pi electrons is away from the group or atom exhibiting mesomeric effect, then it is known as plus M effect. Electron pushing group. Okay. So it is basically electron pushing group or groups with lone pair. Groups with lone pair of electrons. So let us look at an order of the order of this effect. We have O, H, which is there, greater than O, R, greater than NH2, greater than NH, CH3, greater than N, CH3, CH3, which is greater than the halides, greater than hydrogen, greater than not hydrogen, greater than SH, SH, greater than CH2, greater than O minus, greater than NH minus. Okay, so this is the order of the plus M effect. Next we move to the minus M effect. Minus M effect. Minus M effect is basically electron pulling groups. That if the transfer of electrons is towards a group exhibiting mesomeric effect, then that group is said to have minus M effect. So the order is N double bond O, O minus, greater than, this is a plus sign, greater than the cyanide group, greater than the COH group, greater than COOR group, greater than the amine group, greater than the keto group. Okay, they at least contain a double bond or a triple bond generally. The order of minus M effect would be this is the order of minus M effect. So after this we move to the strength of the plus M and minus M effect. So the plus M effect is generally stronger than the inductive effect. Inductive effect is very weak as compared to the resonance effect. Resonance or mesomeric is greater than inductive effect. So always we take into consideration resonance and inductive effect if it is present in the compound, but inductive effect present along with these would be negligible. Okay. Hyperconjugation. Hyperconjugation is another effect. It is basically the dislocation of sigma electrons and not pi electrons. So what are the characteristics of hyperconjugation? Number one, it is spatial type resonance for sigma electrons. Second point is it occurs in case of carbon-hydrogen bond. Okay. And the third point is the carbon-hydrogen bond is in conjugation, that is, it occurs along with an unsaturated carbon. What are the various unsaturated carbon forms in which hyperconjugation can occur? They include carbocation, carbon radical, double bond C, and also triple bond C. Okay, so these are the various unsaturated carbons for which hyperconjugation is possible. So let us look at the mechanism of hyperconjugation, how it occurs. So hyperconjugation. Let us take this compound H2C, double bond C, H, single bond C, connected with 3 hydrogens. So we look at hyperconjugation for this particular carbon, and for this particular carbon, number of hydrogen is equal to 3. Okay. So what happens is in hyperconjugation is basically this bond will fall here and this will open up. Okay. So what do we get? We get H2C, single bond CH, double bond C, H, H. Now this bond has broken off, so we get a minus sign here and we get a plus sign here. Okay, so we get a minus sign and we get a plus sign here. Sorry, we don't get a plus sign here. We get the plus sign on the hydrogen which has broken off, because this carbon is neutral carbon. This carbon is still neutral because it has 4 hands. Okay. So this is how hyperconjugation occurs. Now, due to strained overlap in hyperconjugation, in this case it is a strained overlap. Due to strained overlap in hyperconjugation, hyperconjugation is weaker than resonance. Now, I'll mention the relative strength of all the effects now. How, as in which one is the strongest, and then the order of their strengths. So, the strongest is the mesomeric effect, as I have already stated earlier. Then greater than the mesomeric effect is less than the mesomeric effect is hyperconjugation. And even less than this is the inductive effect. Okay. Now, for hyperconjugation, there should be at least 1 alpha hydrogen. Condition for hyperconjugation is at least 1 alpha hydrogen should be present. What is meant by alpha hydrogen? Alpha hydrogen is the hydrogen attached to the group next to the unsaturated carbon. So in the previous case, this is the alpha carbon and these are the alpha hydrogens. Okay. Now we look at an example of determining the number of alpha hydrogens. So question. So let us take this compound. It's a 6-member ring with an unsaturation here and a methyl group here. We have to determine the number of alpha hydrogens. So this is an unsaturated carbon and this is an unsaturated carbon. These two. Now with respect to these two, the alpha carbons are this, this and this. Now for this alpha carbon, let's name it 1, this is 2 and this is 3. So alpha carbon 1 has 2 hydrogens attached to it. Alpha carbon 2 has 3. Alpha carbon 3 has 2. So in total we have 7 alpha hydrogens. Now this is pretty easy to understand. Now this marks the end of hyperconjugation. It is very easy to draw the hyperconjugation structures once we know the concept, but a question like drawing hyperconjugating structures is not going to come in a JEE type examination, which is basically multiple choice. And so this is the end of the topic of hyperconjugation. Next we move to Bread's rule. Bread's rule. Now what is Bread's rule? sp2 hybridization of bridge-headed carbon isn't possible in a cyclo compound unless one ring contains at least 8 carbon atoms. So let me write it down. sp2 hybridization of bridge-headed carbon is not possible in a cyclo compound unless one ring contains at least 8 carbon atoms. Okay, so what does this mean? Let us look at a few compounds. Let's say this. This, the plus sign here, and this with a plus sign here. Now let's name these compounds as A, B and C. This is A, this is B and this is C. Now in this case the order of stability would obviously be B greater than C greater than A. sp2 hybridization, carbocations are sp2 hybridized, as we know, and there was a plus sign here as well. So carbocations are sp2 hybridized. Now since carbocations are sp2, so since they are sp2, therefore in the bridge position it is not possible, and there was this methyl group on top of which there was a plus sign. So In the carbocations, it is not possible to have sp2 configuration, so A is obviously almost impossible to exist at the bridgehead position. B is the easiest of them all because there is no strain and it is away from the ring, it is away from the bridge position, and C is near the bridge position, so there will be some strain. Okay, so it is B greater than C greater than A. A question like this is pretty common in the JEE type examination, where you will obviously be confused as to how to determine the stability. So whenever it is that question, always think about the hybridization of the carbon. If it is carbocation, it is sp2 hybridized, and sp2 hybridization cannot exist at the bridgehead form, at the bridgehead position. Okay. Now we look at the stability of alkenes. This is another important topic, stability of alkenes, and it's a pretty easy concept, and it's something which you can get confused if you do not understand the meaning of the terms present here. So we have carbon double bonded systems, and we have methanes attached to them, methyl groups attached to them. Due to hyperconjugation, pi electrons delocalize in the system, so that the stability of alkenes increases. More the number of alpha hydrogens, more the stability of alkenes. More the number of alpha hydrogens, more is the stability of alkenes. Okay, when the number of alpha hydrogen is same, then we look at whether it is cis or trans. Trans is always more stable than cis in this case. So this is one point. The second point is, if number of alpha hydrogen is same, then then trans isomer is more stable, because in case of trans, the steric inhibition is less. No, so this is the point of stability of alkenes. So let us look at an example. So say we have this alkene, the one mentioned above, and we have this alkene. Now, so which is more stable? Now, in the first case, in A, there are 3, 3, 3, 3. There are 12 alpha hydrogens. But in this case, there are 3 plus 3, 6, plus 1, 7, and plus 1, 8. 8 alpha hydrogen. So A is more stable than B, because the number of alpha hydrogen is more in case of A. Aromaticity is the next topic which we are going to see. What are the criteria for aromaticity? Number 1. Aromaticity happens for molecules or ions or systems which are cyclic or planar. So, cyclic or planar molecules, ions or systems. Second criteria. Each atom in the ring must contain at least one unhybrid p orbital, so that the hybridization of each atom of the ring must be sp2, or it can be sp also in some cases. This is possible for large rings. So let me write it down. Each atom in the ring must contain at least one unhybrid p orbital. Now, so this makes all the hybridization of the atoms in the ring to be sp2 or sp. Okay. The next point is pi electron in the ring must be delocalized. So this is basically a form of resonance. Pi electrons are delocalized. Number 4. The compound must follow Huckel's rule. What is Huckel's rule? Huckel's rule basically states that the compound must have 4n plus 2 pi electrons. Compound must have 4n plus 2 pi electrons. Here n belongs to 0, 1, 2, 3 and so on. Okay, so it's n is a set of whole numbers. Now, having said that, let us look at an example. Say we have this compound. Okay. So we have this compound and the double bonds are present in these positions. So is it aromatic or not? It is not aromatic. The reason is this carbon here and this carbon here, they are sp3 hybridized. So the electron can jump from here to here, this can jump from here to here, this can jump from here to here, but there is no further jumping because these are sp3 hybridized. Okay. Now, one important point about Huckel's rule is applicable only for monocyclic systems, not for bicyclic systems or tricyclic systems. Huckel's rule is valid for monocyclic systems only. Okay. However, in case of polycyclic rings, peripheral rings should be conjugated containing 4n plus 2 pi electrons. So for polycyclic system, the Huckel's rule is applied to the peripherally conjugated ring. For polycyclic system, the peripheral ring should be conjugated. Containing 4n plus 2 pi electrons. Okay. So this is it about aromaticity. Now the criteria for anti-aromatic system. So there is aromaticity and there is anti-aromaticity as well. So what is the criteria for anti-aromatic systems? Criteria for anti-aromatic systems. Now this is fairly important because in the exam you can be asked, you can be given 4 compounds and asked which of them is the most stable, or arrange them in the order of stability. So in that case, you'll have to figure out one of them or two of them will be, one of them at least would be anti-aromatic, and that will be the least stable. So anti-aromatic compounds are very unstable. In this case, the rule is it must contain 4n pi electrons. Okay. Second is the molecular ion system must be cyclic or planar, which is the case with the previous one, and also each of them should be sp2 hybridized, and the pi electrons in the ring must be delocalized. So all other rules from the aromatic systems are valid here. Now, there are compounds which are neither aromatic nor anti-aromatic. Say ethane. Ethane is neither aromatic nor anti-aromatic. So it is called non-aromatic compound. Okay. So the order of stability is aromatic, stabler, then non-aromatic is much more stable than anti-aromatic. Okay. Acids and bases is the next topic for organic chemistry. Here we will cover the strengths of the conjugate acids and conjugate bases and their relative stability. So, first we'll begin with acids. Now, in case of acids, let's take an acid HA which dissociates to give us H plus plus A minus. So, what is the dissociation constant? The dissociation constant would be H plus concentration multiplied by A minus concentration divided by the concentration of the acid HA. So this is the dissociation constant. Now more this dissociation constant, more is the acidic strength. Ka increases, acidic strength increases. The reason for this is that when Ka is high, the concentration of A minus would become higher, and hence it will be more stable. Thus the stability of the carbon ion or the anion decides the acidic strength. The stability of the carbon ion decides the acidic strength. Okay, and I'll just cover this in more detail in the physical chemistry. But just so you know, pKa is equals to minus ln Ka. Okay, so this will come in handy in this part of the syllabus as well. Okay, so next we move to stability of the conjugate base of an acid. Stability of conjugate base. Now, if A minus is associated with an electron withdrawing group, then its electrons will be pulled away from each other. And if A minus is associated with an electron donating group, then its more electrons will be pushed towards it. So, an electron withdrawing group will decrease this minus charge on the A minus and therefore make it more stable, less stable in this case. The reason is the electron cloud on A minus, as it increases, it becomes less stable. Also, in this case, the acidic strength is higher. And in this case, it is low, decreases acidic strength. Now, this can be deduced on behalf of the fact that the electron withdrawing group increases the stability on the anion, while the electron donating group decreases the stability on the anion. That is the conjugate base. Okay. Now, as I said here, the electron withdrawing group increases the acidic strength because electrons withdrawing group stabilizes the conjugate base. So I and minus M effects showing group have high increases the acidic strength. So let me write that down. Groups with minus I and minus M effect increases acidic strength. Okay. Now, the electron releasing group in the acids will decrease the acidic strength. So, plus M and plus I will decrease the acidic strength. So, vice versa is also valid. Now, say let's do an example now of acidic strength. We have to write the acidic strength order for the following compounds. Acidic strength order for the following compounds. So the compounds given to us are, we are given ethane, we are given ethene, I'm sorry, this is not ethane. We are given ethane, we are given ethene, and we are given ethyne. Okay, so just to remove confusion, I'll write these. Although it's pretty easy to understand that these are the structures for ethane, ethene, and ethyne. So we are given these three compounds and asked which of them has higher acidic strength and which has low. So we have to arrange them in the order of acidic strength. Now what happens is, because of the stabilizing effect, that is the minus I effect, is more prominent in the triple bond. This has minus I effect high than in the double bond and the least in the single bond. So the stability of the conjugate base is of this form: CH triple bond C minus greater than H2C double bond CH minus greater than H3C single bond CH2 minus. And this again implies that the acidic strength order is C greater than B greater than A. Okay. Let's look at another example just to make the point clear. Okay. Another example. Say we are given these compounds. Benzene ring with a methyl group on top. A non-aromatic ring with a methyl group on top. This, and finally there is no double bond present. So these are the four compounds which are given to us: A, B, C, and D. We have to find out the strength of their conjugate base. We have to find the acidic strength. So what do? Now, more the delocalization of the negative charge, greater is the stability. So we assume that the hydrogen is being taken away from here. So the hydrogen goes from here. So we get a negative charge here, here, and here. Now this negative charge can delocalize inside this ring. In this case, it can go inside the ring. This can fall here. And so on and so forth. So this will happen, and there is a greater delocalization. In this case, if it falls here, this will fall here, this will fall here, and no more. In this case, still there would be some delocalization, but in this case, there is no delocalization. Hence, this is much more stable than this, and then this. So, A greater than B, greater than C, greater than D is the order of acidic strength. Now that we know how to determine acidic strength, we are going to look at an example. We are going to look at an exception of this thing, which is used very commonly in the examination to confuse the students. So the topic is steric inhibition of resonance. Now, what is steric inhibition of resonance? So let us take benzene again with a group G on top. Now this G, say, is a planar bulky group which can show mesomeric effect. So G is a planar bulky group showing mesomeric effect. Okay, now we can also have another group G1 here at the ortho position, and this group G1 this group G1 also shows some effect or does not show any effect, so that does not matter. Now in the presence of these groups G1, the mesomeric effect of the bulky group becomes unfunctionable due to the steric fact that G, the bulky group, goes out of plane. So, as we said, G is a bulky group and G1 is also present here. So, between these two groups, there will be some interaction. Now, since they are both heavy groups, therefore they will push each other away. Hence, G goes out of plane from the benzene ring. Now, as G goes out of plane from the benzene ring, so its electrons cannot delocalize in the ring. So, in turn, it means the mesomeric effect of G does not happen. The mesomeric effect does not take place. Okay. Now, so the steric inhibition of resonance, let's see an example of this. So in some compounds, groups having mesomeric effect don't participate in resonance due to steric reason. This is known as steric inhibition of resonance, as I shown in this concept. Now let us look at an illustration of this. Illustration. Say we have this compound. This is the benzene ring. This is the N double bond O minus, that is NO2 group, and this is the CH3 here present. Now, here the CH3 are small spherical groups. So taking them out, talking of them going out of plane to reduce repulsion is absurd. So, as I mentioned previously, one of the groups will go out of plane. Now it was bulky group. Why can't the CH3 go out of plane? The reason is, if it goes out of plane, there will be still high repulsion. If CH3 goes out of plane, the reduction in repulsion is not very high. Is not high. Whereas if the NO2 group, which is much more bulkier, goes out, then it is very high. So this is the reason the NO2 group will go out of plane, and now NO2 group shows mesomeric effect, and that mesomeric effect will not take place in the benzene ring. So having said this, now we look at the acidic strength of benzoic acid and its derivatives. Acidic strength of benzoic acid and derivatives. Now, benzoic acid is this. This is benzoic acid, C double bond OH. So, benzoic acid is obviously less stronger than formic acid. It's less acidic than methanoic or formic acid because of the plus M effect decreases the acidic strength. The COOH group, this group, it exhibits plus M effect. The plus M effect decreases the acidic strength. So, benzoic acid is less stronger than formic acid, which is COOH, HCOOH basically. So, this is the first in the acidic strength of benzoic acid. Next is the ortho effect. Ortho effect. What is ortho effect? Ortho effect basically means the substituent attached at the ortho position in benzoic acid increases the acidic strength irrespective of its electronic effect. Okay? Now, the substituent attached in the ortho position, which is the COOH, out of the plane, so that the plus M of the benzene, plus M of the OOH is reduced, and hence the acidic strength increases. Now, as we saw here, because of the COOH group, the acidic strength is low. Now, let's say we have something like this. We have the COOH in this position, and I'll introduce a methyl group here. Now, as we saw previously, because of steric inhibition of resonance, this COOH group will go out of plane. Now, as it goes out of plane, the plus M effect of COOH group reduces. Plus M effect reduces. Now, as this plus M effect reduces, the acidic strength increases. So, ortho effect basically means that if there is a group at the ortho position in benzoic acid, the strength is high, is higher than benzoic acid. Okay. So let us look at an example of this question. We have to write the acidic strength order of the following compounds. Acidic strength order. of the following compounds. So the first compound is, we have the benzene ring, CH3, C double bond OH. Second is the simple benzoic acid. The third is, we place it at the meta position, the CH3 group, COOH. And the fourth is, we place it at the para position. Which of these is the strongest? And arrange them in the order of acidic strength. So this is the question. Now, the first one is obviously the strongest because of the ortho effect. Ortho effect makes it stronger than all three of them. So that is established. Now, in the third case, the CH3 group has plus I and hyperconjugation. Plus I and hyperconjugation. So, and here again, CH3 has plus I and hyperconjugation. So, which of them would be stronger? Now, the stronger one would be ortho. The stronger one in this case would be C. That is at the meta position. The reason is, at the meta position, this COOH groups electrons can delocalize, and therefore it will inhibit the plus I and the hyperconjugation of the CH3 group, and hence the strength order is A greater than B greater than C greater than D. Let me state the reason again. The reason is, at the meta position, the COOH groups electrons cannot delocalize, and therefore the CH3 groups' plus I and hyperconjugation effect is negated in some sense. Okay. Next we move to bases. In case of bases, we'll look at the conjugate acid strengths. So bases are amine and its derivatives are organic bases. So let us look at say B with a lone pair added to an H plus will give us B plus H. This is the conjugate acid, and the constant rate and the value of Kb is B plus H divided by concentration of B and concentration of H plus. Now, higher the value of Kb, more is the basic strength. As Kb increases, basic strength increases. The reason is for this, the pKb value is more. For the pKb value increases. As Kb increases, the pKb value will decrease. So pKb is actually this. Negative ln of Kb. Okay. So as the Kb value increases, pKb decreases, and then the basic strength increases. Now, for a good organic base, the pKa value is higher for the conjugate acid. For a good organic base, the pKa value of conjugate acid is high, which means it is more stable. The conjugate acid is more stable. A good base is one in which electrons are easily released. So, like we did in the example, in the case of acids, we'll determine which effect will increase the basic strength and which will reduce it. So, for a good base, electrons are easily released. What does this mean? The electron releasing capacity increases the basic strength. And so, plus I plus M and hyperconjugation increases the basic strength. That is, B attached, the base attached to a electron donating group, and vice versa is also applied. Minus I minus M decreases the base strength. P attached to a electron withdrawing group. Okay. The factors affecting are this. Now, there are no exceptions, like in the case of acids. For benzoic acid, the ortho effect is taking place, and also there's steric inhibition of resonance. In these cases, there is no such exception, and therefore, if we follow the theory properly, we can come at the right answer. So there will be no questions about exceptions in this base thing. Next, we look at tautomerism. Now, if you remember, I had said about tautomerism while discussing about isomerism in general, and I said that this is an important topic and will be covered in detail in the subsequent lectures. Now, tautomerism is a form of structural isomerism in which are interconvertible to each other due to oscillation of an atom between two polyvalent atoms. So it sounds confusing, so I'm going to write it down. Structural isomers which are interconvertible to each other due to oscillation of an atom between two polyvalent atoms. So let's say we have something like this. We have X joined with Y, double bonded joined with Z, and there is this hydrogen group attached to X. Now this can interconvert to X double bond Y, single bond Z with a hydrogen attached to Z. This is a triad system as the oscillation takes place between 1 and 3. Okay. Now if the oscillation is between 1 and 2 atom, then tautomerism is known as a triad system. 1 and 3rd atom, then tautomerism is also known as the triad system. So we'll basically focus on the keto-enol tautomerism. Keto-enol tautomerism. So what is keto-enol tautomerism? It looks something like this. We have a keto group, CH2, C double bond O, CH3, and there is a hydrogen attached here. Now this hydrogen will fall here and this will open up, and so we'll get something like this. We'll get CH2, double bond C, single bond CH3 with the O and hydrogen attached to this. Okay, so this is the enol. Enol because there is a ene group, that is a double bond group, and ol, that is the alcohol group which is attached to it. Now, in general, the keto part is more stable. In general, the keto form is more stable. Now, what are the conditions for a compound to show tautomerism? There are various other types of tautomerism possible as well, but those are not very important. We'll look at ketoenol in detail more, but now conditions to show tautomerism. For a compound to show tautomerism. The first condition is the compound must contain electron withdrawing group like nitro, keto, cyano, and eneans, etc. Compound must contain electron withdrawing group like nitro, keto, cyanide, etc. Okay. The compound must contain at least one alpha hydrogen. At least one alpha hydrogen or acidic hydrogen. The acidic hydrogen cannot necessarily be alpha hydrogen. So, what does this mean? This means basically if we have CH2 single bond CH with a double bond here, this is the keto form, and there is a minus here. So this minus can fall here, and this can open up, and so this compound is resonance stabilized. So what is acidic hydrogen in this case? In this case, there is no acidic hydrogen because the negative charge is delocalizing. But say we have say we have a compound of this form. We have CH3, CH, double bond CH, C double bond H. So this hydrogen here is acidic. The reason is this can be easily lost and resonance can take place. How? In this form. This hydrogen will move out. This double bond will fall here. This bond will fall here. So what do we get? We get something like this. CH2 double bond C H single bond CH double bond C H O minus H plus. So this is the compound we'll get in this case. The alpha carbon must be sp3 hybridized. Keto in all systems. So how it takes place and which of them is more stable and which exists in major form. So I have already shown the example of keto in all systems. The keto in all system can be catalyzed by a H plus or OH minus. Even any other tautomeric system can be catalyzed with an H plus or OH minus. So can be catalyzed by an H plus or OH minus present in the medium. So let us look at the acid enolization, acid catalyzed enolization. Acid catalyzed enolization. This acid catalyzed enolization. So we have a compound CH3, C double bond O, CH3, propanol. Now, if we provide H plus, it becomes H2C double bond C, OH, CH3. So basically it goes through the enol form. How does it take place? Let us look at the mechanism of this thing. So first, this O here has lone pairs attached to it. So these lone pairs will be attached to this hydrogen. This hydrogen will basically attack this lone pair, and so we'll get something like this. CH3 C double bond OH plus CH3. Okay. Now what will happen is this this OH here is a double bonded form. So this will fall here. This will fall here, and one of the hydrogens from here will fall here. So how does it happen? We have H2C double bond C single bond OH with a CH3 and a plus sign and a plus H plus. So this is basically this compound. And so this is the mechanism of acid catalyzed enolization. There is base catalyzed ketonization, which is the reverse of this, and which is pretty easy to understand. So if a keto compound tautomerizes to form more than one type of enol, then the enol which will be a major product which is more stable, that is, which has more alpha hydrogens. So that is a very easy concept which is very easy to understand from the stability point of view. Next we move to ring expansion. Ring expansion. So let's say we have something like this. And there is a methyl group attached here. So what happens is, in this case, this bond here will open up to fall here. This will attach, and there was this plus sign here. This was a carbocation. So this will attack here. Ring expansion takes place only when the outsider is a carbocation, and this will fall here, and this will also attack here, and we will get something like this. This is the CH2 group, so it forms basically something like this. So the plus sign would come here, obviously. There is a plus sign here. This is the plus sign here. Okay. This is basically ring expansion. It takes place in case of compounds. It takes place in case of compounds which have carbocations outside the ring. Now let us look at an illustration of this. Okay, so let's say we have this compound. We have a 5-member ring, and on the outside we have CH2OH attached to it. Now let's say we provide H plus and dehydration. What will happen is that this OH group will fall out. The H plus here will attack the OH group and take it away. So we'll get something like this. We'll get a carbocation here, CH2 plus. Now this carbocation would then form by ring expansion this. And now there was a hydrogen, and there is a hydrogen here. So this hydrogen will fall out by elimination due to the heat, and what we get is this. Final product is a 6-member ring with a double bond here. Okay, so that was dehydration with ring contraction and expansion. So this was a form of ring expansion. Now let's look at a form of ring contraction. Okay, what happens is, I'll show it by an example. Let's say we have this compound, we have a 6-member ring, and on this carbon there are 2 methyl groups attached, and there's a OH group here. So if we provide H plus and heat, what happens is we'll get something like this. The carbocation will form at this position plus this and this. Now this methyl group will come here and it will form this. This methyl, this is the migration part of this. This is the methyl, and there is a hydrogen here as well, and there are hydrogen here as well. Now the major product in this case would be this. This is also methyl. So the major product in this case will be this double bond, this and this. So the migration has taken place and these double bonds will form. And there's this plus sign here, obviously. Sorry, I didn't mention that. This is a plus sign here, due to which the ring expansion will take place actually. This will fall out. So if this falls out, then this is formed. This is the major product. Why major product? Because it has 10 alpha hydrogens, which is much more stable. Another form in which it can fall is this hydrogen falling here. So if this hydrogen falls here, the compound we get is this. CH3, CH3 and this. So in this case, how many alpha hydrogens do we have? We have 2 plus 1, 3, and so we have 3 alpha hydrogens in total. In this case, we have 6 alpha hydrogens, and another form is we can also get the compound this from this. This is the double bond, and this is CH3. So this compound is also possible if we eliminate the hydrogen from this methyl group here. Okay, so in this case it has 3 alpha hydrogens, so this is the least stable possibility. Now if we have this compound, so I was about to illustrate ring contraction, so let's do that now. So if you have this compound, another possibility is that after the formation of the carbocation, that is after this happens, this hydrogen here, they move out and this carbon gets attacked here. Okay, this carbon gets attacked here and this will fall here. So what do we get? We get something like this. This and this methyl group, this methyl, and externally we have a plus sign here, and this is about to form. So we get something like this, and this is breaking off. So we get this, a 5-member ring with a C here, methyl attached to it, and a plus here. So after alkene formation, it will look something like this. The most stable product would be this. See, this is the ring contracted product. So what can be the question which can be said on this? You can be given this compound here and asked how many products would be formed upon adding H plus and heat to this compound. So your obvious guess would be 3 products, in case you get 3 products by, going through this analysis here, that is this, this and this, but you will forget about the ring contracted product. So always make sure that whenever a carbocation is formed and the carbocation is inside the ring, then ring contraction is another possibility which you have to take into account. And this product will be present at least in 1/3 amounts. Okay, since it is a little more stable than the 3 alpha hydrogen product. Next, we look at halogenation. What is halogenation? Halogenation can have both syn and anti-addition. So, first I'll tell you about syn and anti-addition. What is meant by syn and anti-addition? It will be used in a lot of mechanisms we will go through. Syn and anti-addition. C double bond C, R, R. So we have groups attached to this double bond system. So syn addition would basically mean if an AA group, it attacks this carbon on the same side. So this is syn addition. And it will form a product of this manner. So in the Newman representation, it will look something like this. A, R, R, R. In anti-addition, one of them would attack from this side and the other one will attack from this side, and the product we will get is this. This is R, R, A obviously, and here we'll get R, R and A. This is anti-addition. This is the eclipsed form and this is the staggered form. Now as you know, staggered is more stable than eclipsed, and therefore the anti-addition is much more efficient and stabler than the syn addition. So in case of halogenation, what is the mechanism of halogenation? So in case of halogenation, we have anti-addition. That is the first point which you have to take into, which you have to remember. Now we have R, CH, double bond CH2, to which we are saying adding bromine, CCl4 solution. Okay, CCl4 solution is added because the reaction takes place better in a polar situation. So what do we get? We get a compound this. The bromine here, CH2, the bromine here. I'm sorry, this bromine would be here above. Here the bromine would be here. Okay, how does it take place? The mechanism of this thing is we'll have a Br minus. Now that Br minus, sorry, not Br minus, we'll have a Br attached to another Br. So this is the bromine group, and it has a lone, empty orbitals. So this double bond will open up, and this carbon would attack this bromine, and this bond will fall off. So we'll get this. We'll get R, CH plus CH2 with a bromine attached, and now this is a plus group here, and we have a Br minus. So this Br minus is also present in the system. Now this bromine here has a lot of lone pairs. Now this lone pair here would form a bridge with this CH here. So we get R, CH, single bond CH2 with a bromine bridge. Now this bromine bridge helps stabilize this intermediate. Now since this intermediate is stable, the other bromine can attack, and this will fall off. So this is Br plus obviously. So this will fall off, and what we get is this: R, CH, Br, CH2, Br. Okay. Next we look at free radicals. Free radicals. Now, free radical is of this form. We have H here, H, H, and a lone electron here. Not a lone pair, but a lone electron. So this is sp2 hybridized free radical. So in case there are H's attached to it, it is sp2 hybridized free orbital. As we progress, if we attach fluorine to here, fluorine in place of hydrogens, then this becomes sp3 hybridized p orbital, sp3 hybridized radical. The free radical are sp3 hybridized when attached to an electronegative group, that is the electron withdrawing group, or it is at the bridgehead position. Free radicals are sp3 when number 1 attached to a more electronegative or electron withdrawing group. The second case is at the bridgehead positions. Okay. The free radicals are basically electron deficient, so they are electrophilic. Electron deficient, so electrophilic. Second is they have a septate of electrons. Third is they are paramagnetic. Okay, and also they have both sp2 and sp3 hybridization possible. So let us look at the stability of free radicals. So CH3 free radical is much less stable than CH3C, CH3H free radical. The reason is these are electron donating groups, and so this carbon free radical, which is electron deficient, it gets electrons from this electron donating group here and here. This has a basically plus I effect, and therefore it becomes more stable. Next is CH3C free radical, CH3, CH3. This is more stable again because of the triple inductive effect. Then we have CH2, CH, double bond here, CH2 with a free radical here. This is also because of the electron inductive effect of the double bonded system. Now this is less stable than attached to a benzene ring, free radical, and this is again less stable than attached to two benzene rings. And this is less stable than attached to three benzene rings. Okay. So this marks the end of general organic chemistry and some part. Now we'll look at the various reactions mechanisms of various compounds like alkanes, alkenes, alcohols, esters. I'm not going to cover all of them because they are cumbersome and they are not very relevant. You have to learn them, know them by heart. For the purpose of this video, I'm going to cover the important ones, the ones I feel are more important than the others and which have been debated many times in the JEE papers. Okay. Words reaction. Now, Words reaction is particularly important because in this case we can get many forms of products, and the question can be set as to how many products are possible in this reaction. So the mechanism of Words reaction is we have an alkyl halide, and to this we add sodium, and we have another alkyl halide. So these part, it goes away, and what we are left, the reaction takes place in dry ether. We are left with the RR group and obviously 2NaX compound. Now, there are various mechanisms possible, so we'll look at all of them. The first is the free radical mechanism. Free radical mechanism. In the free radical mechanism, we have the sodium free radical. To this, we have attached we have Rx in the system. So what happens is NaX gets formed and we are left with the R free radical. Now there are many such R free radicals in the systems, and so they join together to form RR, that is the alkane. Also the steric factor for 1 degree is greater than 2 degree is greater than 3 degree, and therefore RF formation is less than RCl, is less than RBr, is less than Ri in this case. Second type of mechanism we look at is the ionic mechanism. In the ionic mechanism, we have the Rx group and we have 2 electrons in the system. So it forms X plus R minus. Okay, so this is formed, and then we also have Rx in the system. So this will attack here and this will move out. So what we are left is with an RR group. Now the sodium, how does this electron come in the system? We have 2 sodiums, so they form 2Na plus these electrons. Okay, so actually sorry, I'm really sorry, this is X minus and this is R plus. Okay, now here also the order of formation is 1 greater than 2 degree greater than 3 degree, that is RF is formed lesser than RCl, is formed lesser than RBr, is formed lesser than RI. The ether is used in the dry form because the moisture reacts with the sodium. Okay. Now, on addition of oxygen, the rate decreases, but still the reaction goes on. Okay, this reaction runs parallel both in free radical and ionic mechanism. This can be a pretty important concept here. If you must be wondering which of these mechanisms is more valid. It states that both these reaction mechanisms take place simultaneously in the system. So we'll have many intermediates present in the system. We'll have the R free radical, we have the R carbocation, we'll have the X minus, we'll have the X free radical, we'll have the sodium plus and the electrons. We'll have a lot of things in the system. Okay, now the Words reaction is not a good method to prepare unsymmetrical alkanes, that is of the type R bar. The reason is, in the Words reaction, if we try to form R bar, how do we go about it? We place Rx plus 2Na and R bar X in the system. So it will expectedly give us RR bar. But the system contains many Rx's and many R1X's as well. So it will also give us RR and R bar. So these are also the possibilities. So it is very difficult to separate them. Hence, this is not a good method to prepare unsymmetrical alkenes. Okay. Next is the Grignard reaction. Grignard reaction. What is the Grignard reaction? Grignard reaction basically involves the formation of Grignard's reagent. So we have the free radical mechanism here. In the free radical mechanism, we have Mg plus Rx forming RMgx, that is Mg with the electrons on these Mg free radical plus R bar plus X bar will give us RMgx. So these are the electrons of Mg, these are the electrons of R, and this is the electron of X. So this is the free radical mechanism. So next we have the ionic mechanism, which makes more sense. We have Mg forming Mg2 plus 2 electrons, and we have Rx plus 2 electrons giving us R plus X minus. Now this R plus will react with the Mg2 plus and the X minus. Okay, this R plus will react with the Mg2 plus and this will be R minus. This will be R minus since there are 2 electrons involved here. So this R minus will react with Mg2 plus and X minus to form RMgx. This is the Grignard reagent. Now, in case of the Grignard reagent, what does actually happen? Now, this Grignard reagent does not form in case of if there is any moisture present in the system. So that is another important thing. Now, this Grignard reagent is very important in imparting the R group to other compounds. So, let's say we form the Grignard reagent. Next, what? We react this Grignard reagent to a compound Mg to the compound. Say we are here to form alkenes, right? So say we have this Grignard reagent CH3 MgCl. Now if we react it with CH3 Cl, what happens is it will form CH3 plus MgCl2. Now this can be used a lot. The reaction takes place in the presence of ether, EtO2. So this is very useful in preparing alkanes, and a lot of alkanes are prepared using Grignard reagent. Okay. So these are the reactions which I think are important in case of alkanes. Now we move to the pinacol-pinacolone formation. Pinacol formation. What is a pinacol formation? We have R, C, double bond O, R, plus R, C, double bond O, R, and we are reacting it with the amalgam, that is MgHg. Now this Mg has a lone pair here. Now this lone pair here is used to attack these carbons here and here, and what we get is this. We get R, C, free radical, O minus R, plus R, C, free radical, O minus R, and this O minuses, there is an Mg2 plus here which forms a bridge between them. Now, when this Mg2 plus is removed, we get something like this. We get R, C, R, OH attached to this carbon R, OH. So this is the pinnacle. Here Mg has two roles. It gives the electrons and helps in the ion formation, and it also brings the ions together for the collision. Okay, it forms the bridge and brings them together for collision. So let us look at an example of pinnacle reaction. Question: say we have this compound. We have a 4-member ring, ketone, and we give it MgHg. What happens? What happens is we get this product with an alcohol here and an alcohol here. So this is the product which is formed. But the reaction does not stop here. What happens next is this alcohol will move out and we get a plus sign here. Now this carbon here will attack here and this hydrogen will move out. So we get this. There is a ring expansion taking place. This is the double bond O. This is the ring expansion formed. Okay. This is the final product in this case. Next we move to carbenes. What are carbenes and what are their reactions? What are carbenes? Carbenes are carbene is this group. See, with its double bonds, with its hydrogen, two hydrogens attached to it and a lone pair. The carbenes are electron deficient. What are the properties of carbenes? Number 1, electron deficient. They are neutral. They do not have any charge on them. They have a 6th state of electrons. Number 4, they are electrophilic and nucleophilic, both depending on the nature of the substituent. Can be both electrophilic or nucleophilic. And there are two types of carbenes. Singlet and triplet. Singlet carbene and triplet carbene. Singlet carbene, the both electrons are in the same orbital, that is s is equals to 0. And in case of triplet carbene, both electrons are in different orbitals, so s is equals to plus minus 1. That is the magnetic. S is the magnetic spin number. So singlet carbene. Let's discuss singlet carbene now. Singlet carbene, the multiplicity is 2s plus 1 is equals to 1. Multiplicity is 2s plus 1 is equals to 1. It is diamagnetic since both the electrons are in the same orbital. And structurally it is something like this. We have hydrogen, carbon, hydrogen, and in one of them we have this electron pair. This is sp2 hybridized and its orbital looks something like this. Okay, triplet carbene. Triplet carbene has different properties. In the sense, the multiplicity in this case is, here it was 1, here's 2s plus 1 is equals to plus 3 or minus 3, plus minus 3. So when S is equals to 1, it becomes 3. When S is equals to minus 1, it becomes minus 1. So it is not plus minus 3, it is plus 3 comma minus 1. So these are the possible multiplicities. It is paramagnetic because the electrons are in different orbitals, and structurally it looks something like this. We have hydrogen, carbon, hydrogen. These are the electrons present. So by Hund's rule, they'll have the same spin. So it will be positive spin or negative spin. So by this we can have plus 3 or minus 1. So according to Hund's rule, triplet carbene is more stable because of exchange energy. Higher exchange energy, so more stable. Triplet is more stable than singlet carbene. The exception is when M plus groups are introduced, then singlet carbene is more stable than triplet carbene. Okay, the exception is when M plus groups are introduced in the system, then singlet carbene becomes more stable than triplet carbene. Wolf rearrangement. Now, Wolf rearrangement takes place in the following compounds. Following type of compounds are C double bond O, CH, NH, CH N2, not NH, N2. What happens is if you provide Ag2O and heat, the reaction takes place and it forms a singlet carbene, which in turn leads to this. So the singlet carbene is present here with both the electrons here, and this will move out and this will attack here, and the nitrogen is liberated obviously. So in the next step we get this C double bond O, CH, R, and this is known as and this is a double bond obviously, and this is known as captene. Okay, the short trick of Wolf rearrangement is that the group attached with C double bond O migrates on adjacent carbon. The trick is group attached to C double bond O migrates to the adjacent carbon. Okay, here if R is chiral, then there is no restriction on configuration. In simple words, the group as such moves to carbene carbon, and due to its division of a positive charge on the carbon plus a negative charge on the CH, the double bond is formed between the two. Okay, the group as it is migrates to the carbene carbon, and the double bond is formed between the two. This is the Wolf rearrangement. Now, and the next reaction is the reaction of diazomethane. Now, this is a very, very important reaction. What happens in this reaction is we have CH2 attached to a diazo group, and there is a minus sign here on top of it, and N has a plus sign on top of it. So this is the CH2 group, and this is the nucleophile. CH2 minus is the nucleophile here. Now, say we are reacting it with active hydrogen. So we have RCOOH plus active hydrogen. Active hydrogen from this RCOOH, it will basically form R, C double bond O, O minus plus CH3 N2 plus, and this N2 plus will move out and finally we'll get an ester, which looks like this: R C double bond O O CH3. So this is the reaction with active hydrogen. Let us look at another illustration for this. This is a very important reaction because a lot of questions can be asked from this. You can be given various types of compounds with active hydrogen and you can be asked what will be the final product. So let's say we have a compound, this phenol, and to this we are adding diazomethane, H3C N2 plus, H2C, sorry. This is minus, this is plus. So what happens is first we'll form this anion, and we'll have this active hydrogen is present here. We'll have a CH2 minus N2 plus. This in turn will open up, and this will attack here. This will open up and this will be attacked. Sorry, this is CH3, not CH2. This is CH3, and there will be no plus sign here. There will be this empty orbital here. So this will attack here, and this N2 will move out, and finally we'll get anisole, which looks something like this: OCH3. Okay, this is the reaction mechanism. Next we move to Reimer-Tiemann reaction. Reimer-Tiemann reaction. So how does Reimer-Tiemann reaction take place? We have, say, a phenol group, phenol plus CHCl3 plus KOH. So this will form this compound, C double bond O H O H plus, this is the ortho form and this is the para form formed here, CHO OH. This is much more stable than the other one because of the hydrogen bonding which can take place here. Okay, this is the Reimer-Tiemann reaction. If a bulky group is present in the ortho position of the phenol due to strain crowding, now para product dominates. So initially ortho product is the major product. Major, and this is the minor product. But let's say I put a group G here. This is the phenol, and this phenol has a group G here which is bulky, and so the product formed here would be this. This will be the major product, and the minor product would obviously be this. Okay, this is the minor product. The reason is the bulky group repulses the attack from the CHO, and therefore the ortho product, and also the ortho product has a lot of steric crowding at one position. Next we look at Baeyer-Villiger oxidation. Baeyer-Villiger oxidation. In the Baeyer-Villiger oxidation, we have a ketone, asymmetric ketone, and to this we attack CH3, C double bond O, 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 H. So this is a per acid. Trifluoro per acid. So the product formed in this case would be RCOH. double bond O, OR. That is an ester. In short, the oxygen gets inserted between the C double bond O and the leaving group. That is, oxygen gets inserted between C double bond O and best leaving group. What does this mean? Say we have R, C, OH, and to this we attack this per acid. What forms is R, C double bond O, OH, and not the other way around, because hydrogen is a better leaving group than the alkyl group. Okay. So these are the important reaction. Now next, we can also look at the aldol reaction, which is fairly important. Aldol reaction. Now, what is aldol reaction? In aldol reaction, we have a CH3, C double bond O, H, and this has another CH3, C double bond OH. These are combined together, and in the presence of OH minus, this is a reversible reaction, we get CH3, CH, OH, CH2, C double bond O, H. So this is the aldol reaction. The short trick for this reaction is basically combining these two. So we can write it in this manner: H, C double bond O, CH, CH, H2 plus O double bond C, H, CH3, and we remove this part and we get finally this H, C double bond O, single bond CH, double bond CH, CH3. Okay, so this is the aldol reaction. Another form of aldol reaction is Claisen-Schmidt reaction. Claisen-Schmidt, that is cross aldol. In Claisen-Schmidt reaction, the aldol reaction is one in which alpha hydrogen occurs and others doesn't. That is the Claisen-Schmidt reaction. There is alpha hydrogen and others do not occur. So let us look at an example of this to understand this better. We have CH3, C double bond OH plus phenyl, C double bond OH, benzaldehyde that is, and to this we add NaOH and heat, and we get the product this C double bond O, C, H double bond C, the phenyl and the hydrogen group. This is known as a cross aldol reaction. In this one has alpha hydrogen, this one does not have alpha hydrogen. Okay, and yet the reaction is taking place. This is known as the cross aldol reaction. We can look at another example for this. Another example will be CH3, C double bond OH plus something like this, C double bond OH. Here no alpha hydrogen, here we have alpha hydrogen. So in the presence of NaOH and heat, what do we get? We get this. CH double bond C H single bond CHO. Okay, so this is the Claisen-Schmidt or cross aldol reaction. With this, we come to the end of organic chemistry. As I have said, we do not need to cover all the reactions because you have to know the products and the reactions mechanisms by heart and not exactly how it occurs. So, and also I have covered all the various topics. The important concepts have been marked, and so next we move to the physical part and the inorganic part. Thank you.